So this talk will cover a framework written in Python, obviously, which covers the work that me and Marco and have been developed for the past 2 years, approximately, specifically trying to emulate HGCAL firmware trigger primitives, which is the basic building blocks of the CMS online trigger system. So this title is quite long, so for you to understand exactly what I'm referring to, we have to go back to the beginning, which is the High Luminosity LHC, which as far as I know, most of you are familiar with. So essentially, it's an extension of the current LHC, which will bring on one side approximately 4 times more luminosity than the LHC, and also around 200 collisions per bunch crossing compared to the current around 40 or 50 we get on average. If you see the pictures below, we show examples of a real event taken in 2016, actually a very busy event with 86 collisions per bunch. And then on the other picture, we show something similar simulated for CMS for what we expect to see in the future, only showing the endcap calorimeters. So in both pictures, you can see the energy deposits in the calorimeters and see that it's quite of a mess, very hard to reconstruct, and the challenge for the algorithms, especially in the trigger, where most of the data is simply thrown away. Next slide, please. So in CMS, and you can see here a picture where you can see very well the solenoid and the muon chambers in red. And on the right, you can see one of the endcap calorimeters. And here is where we will focus our talk, because among all the upgrades we will, CMS will do, the one for the endcap calorimeters is one of the most significant. So here you have a mock-up of what the endcap calorimeter will look like. It's called the High Granularity Calorimeter, or HGCAL. It's a sampling calorimeter, meaning it has many layers with active material, and those layers are interleaved with absorber. The active material is, for the most part, silicon, especially close to the interaction point of the 2 protons. But it's also scintillator in regions a bit farther away, because scintillator is a bit more cost-effective. And you can also, on the left side, you can see kind of the dimensions of one of the endcaps, 2 meters by 2 meters. So it's quite massive, with lots of active material, lots of sensors with a specific hexagonal geometry, which makes developing algorithms here a challenging thing, especially when you have to then mix the 2 geometries to make it work. And also taking into account the enormous data throughputs involved of the order of 100 terabits each second. Regarding the data flow of trigger primitives, which is what constitutes the building blocks of what comes later in the online trigger system of CMS and what is used to make a decision of whether an event should be kept or not. The data flows roughly as in this sketch. So it all starts in CMS and then in one of the subdetectors, the HGCAL as described. Although all the subdetectors of CMS have their own set of trigger primitives. And then focusing only on one of those layers, a layer with only silicon, to give an example, we can focus then on just a single hexagonal module. So it's nested complexity here. Each of the modules has many chips, which are dedicated chips just for HGCAL, which process all the data involved and then send that data to other chips still located on the detector. And finally, all this information is sent off detector to racks, which have some boards running all the firmware, all the algorithms and firmware in FPGAs. And this backend is split into 2 stages, 1 and 2, which are used to build quantities that are used by the level and trigger of CMS to make decisions. And here in this talk, we focus on the stage 2. Which we will present in the next slide. So the idea is that this stage is deployed in the firmware, meaning it's supposed to run exclusively on FPGAs, but it's also available in a C++ bit level emulator, which is supposed to reproduce very closely what the firmware does, and also in a non-bit level simulation, and which is also implemented in C++ and which depends on the CMS official software, CMS-SW. This is one of the reasons why we decided to port this reconstruction chain to Python to make things easier, and I'll go to this in a second. Before, just to give a brief overview of what this chain does, because all these algorithms were re-implemented by us in Python. So it all starts with what we call trigger cells, which represent an aggregate of silicon sensors. So it's just a way of further reducing the information available to make it possible to process this huge amount of data. And we map these trigger cells to a specific space where, and the space is as a function of r over z versus phi, where phi is the azimuthal angle in CMS, and r over z is projective coordinate space, which projects into 2D all the layers of the sampling calorimeter, further reducing the available information. Once this mapping has been done, we bin it, and each bin will hold the energy of all the trigger cells that belong to that bin. And then also to solve some issues with non-uniformities of this energy distribution, we smear the distribution slightly, and then we look for local maxima in this distribution, which we call seeds. To each seed, we associate all the trigger cells that were there in the beginning. And once we have the seeds and the trigger cells, we effectively got the clusters. And so we can build all sort of cluster-related variables, such as positions, energies, shapes, and so forth, which are then sent to the level one trigger. So we did this in Python, which the next slide will show. And the advantages are many. First of all, in my opinion, at least, it's much easier to run, especially since we don't have now dependencies on CMS, on the CMS software, except for the input files. All the rest is done in Python. The code itself is structured, as you can see in the diagram. So we have two main, what we call processors. One of them processes event data, the other one geometry. The one processing event data is a bit more complex since we are dealing with hundreds of thousands of events, and we want the code also to work with pileup 200 data. We want to make sure it's fast. So we only process a subset of events, and only if the user requests for more events, we go back in the chain and process the events that were requested. Otherwise, we just look into the ones that were already processed and stored. And then there's a third block, which we call the client, which is supposed to be completely transparent to the two processes I just described, so that someone that comes from outside, let's say, can develop their own algorithms and connect them with the event and geometry data without actually knowing what the latter are doing. This is quite modular and brings advantages such as much quicker prototyping. When one wants to explore new ideas, new algorithms, it's much easier just to plug some new idea without knowing what the rest of the code is doing, which was not possible in the C++ implementation. And then it's also a bit more friendly for newcomers, which tend to be more familiar with Python than with C++. And finally, if one wants to do parameter optimization, which is the case when doing reconstruction in high energy physics, each stage that I was describing has many parameters that need to be optimized. This optimization is much easier and more conveniently done using a framework fully developed in Python. Since the environment is Python, we use all kinds of known Python packages, which you can see there. Just wanted to mention that the geometry processor that we needed we had to develop a simplified geometry of HGCAL by ourselves to make sure we could display the information that is being processed by the chain. And so this is what I show in the next slide, where we compare the current CMS official geometry, which is done in GM4, and which handles all kinds of information, including material, not only positions, with our simplified geometry, which is only applicable for a visualization. So obviously it's much simpler, much easier to implement, but it still requires a lot of effort and allows the visualization of some of the events we will show next. And here we are showing the two detection technologies. So for this talk, you can go to the next slide, please, Marco, thanks. For this talk, instead of doing a notebook, which we thought didn't really match what we had to show, we instead will do a really quick demo, which people can follow on their own at home, since it might take a bit longer than the time we have here. The idea is that and this can be useful for many people, is that to show the event display we developed, we want for it to be easily accessible in a URL, and also accessible for people eventually not connected to the CERN network. And the way of doing this is using a service provided by CERN called Platform as a Service, which is strongly based on OpenShift. So it essentially runs OpenShift. So although the demo is can only be run as it is by someone with access to CERN, as long as you have some access to OpenShift, it should work as well in a very similar manner. So I think, Marco, you can go there and show a bit how it works. Just in a nutshell, this is the repo we created with the example. The two Python files that you see are the scripts that generate a dummy web app, and this can run locally. And then on top of this, to be able to run this, to deploy this to a specific server, in this case, OpenShift, provided by OpenShift and by CERN, you just need to add, in the most simple scenario, just two files. So one of them is the app.sh, which you can see there, which simply contains the command that you'd run locally. So there it will be Python and then the name of the script you want to run. And then the requirement.txt file, which contains all the packages that you need to install in order to be able to run your application. And this format is probably already well known by people, for instance, building Conda environments somewhere else or deploying packages in pip. The idea is what this does is it grabs your repository, it detects that is a Python, mostly Python, and builds a Docker image for you. So you basically have to do nothing for this to work. And we're going to show this very quickly. If you follow these step-by-step instructions, you'll be able to do it by your own. But if you click on that link, you will be taken to the OpenShift environment provided by CERN, which anyone can access. Really quickly, what you can do is click on the Add button on top. Marco, please. And just import from Git below. So essentially, you specify the URL of your repository, and you type it there, and the system will recognize essentially everything. So Marco will show what happens just in a second. But the idea is that you basically have to do nothing. So here, it detected immediately that this is Python. This is the demo example. Then there are some additional options that we want to explore due to time constraints. But if you go down, you can define the name of your app and other details that really don't change much. Just change, for instance, the URL of your web application. Then you can also specify port information and so on, but usually the defaults are fine. Marco here is choosing a name, could be anything. And then you click on create if you want to deploy your app. In this case, I think Marco already did this before, so we don't need to do it. Just show how it looks like at the end, Marco. If you go to, for instance, this is the demo you'll be able to obtain. So this link is accessible by anyone, and you have all the interaction you want. These plots were done with Dash, which runs Plotly, but you could have done it with other libraries as well. It's really straightforward. And yes, if you go back to the OpenShift website, we can also show just an additional detail. If you go to topology and you click on the app that one is running, you have access to the many builds. When you deploy for the first time, a build is initiated automatically. If you push new changes to the repo, you can start a new build if you want, which will pick the latest commit, and then you can inspect everything that is going on, including downloading packages in the log. And that's it. That's the basic idea. It's very simple to use. And now I'll pass the floor to Marco, which will explore exactly the same idea, but for the full event display that we've developed, with the added benefit that since we are using CERN service, we can actually use its own storage system. So for instance, EOS. Go ahead, Marco.
Hello, everyone. So the web application deployed here has been created using Plotly library and is a more complete example showing the potential of the platform just illustrated by Bruno and its integration with the CERN computing environment. So the web application, which has been built on top of the standalone framework that Bruno presented, allow us to display simulated events in the HGCAL. So here, for instance, we have simulated zero pile-up charge pion, which is you can show here in this picture with a 3D view of the shower. So each small rhomboid represents a trigger cell where some energy has been deposited. So, for instance, the pion here deposits some energy in the electromagnetic section of the HGCAL, then travels in the calorimeter without interacting, and then we have a massive shower in the hadronic section of the calorimeter. The trigger cell, the color code of the trigger cell is based on the energy deposit, and we have here a color bar. But then, as you can see here, we have different opacities in the trigger cell. That's because the application, makes use of the stage 2 RICO chain, which has been presented by Bruno and has been implemented in Python to identify clusters. So, for example, here we have this trigger cell, which has been clusterized, meaning that has been associated to the cluster or seed, which has been found by the reconstruction chain, while this one has not. Okay, now I want to show you this event, which represents a 200 pile-up photon in the HGCAL. So we have a photon that enters in the HGCAL with these coordinates for eta, phi, and t. We have here the main shower of the photon, which is surrounded by many trigger cells, which has been hit by pile-up particles. And then we have many showers that have been wrongly identified. Then to better highlight this fact, we can switch into this figure in which we have the same trigger cells, but with a different color code, because here the trigger cells are colored depending on the stage 2 reconstruction cluster index. And so we have this purple in the center of the figure, which is, and so all the purple trigger cells are the ones that have been clusterized with the main shower. But then we have other secondary shower, which has been incorrectly identified by the stage 2 reconstruction chain. Then I want to show you the app running. And so here we have a zero pile-up photon in the HGCAL. As you can see, you have the rhomboids, which are the trigger cell, and the main, the core of the shower, and all the layer. The most interesting case is to look at the 200 pile-up event. This is again photon, and so we have in the center of this figure, we have the main shower, the main so the one generated by the gen photon, and then we have other clusters. Then we can switch into the into this image in which in different color we highlight different clusters, and again we have the main cluster and two other clusters, which has been incorrectly identified by the chain. Now we are using what we call default chain, which is the stage 2 reconstruction chain that has been implemented in Python. But then, due to the flexibility of our framework, it's very easy to implement other reconstruction chains. And for example, we develop what we call the core seeding chain, which makes use of non-projective coordinates. And as you can see, with this new chain that has been implemented in Python and can be run live, we have just one cluster in the same event, which has been identified. So which is a great result, since we are deleting majority of the cluster due to pileup. Then going back,
I'd like to comment that if you want to have questions, you should be wrapping up soon. Okay. Looks nice, by the way. Feel bad about interrupting.
Then another so with this tool, we can also tune the current chain reconstruction chain parameters. For example, what we call clustering radius. So as Bruno explained, for each seed, we so after identified a seed, the reconstruction chain associate some trigger cell to that seed, and this is done with a geometrical matching between the seed and the trigger cells. So we can modify through the app. We can modify the radius of the clustering, and so, for example, here you have the maximum available radius, and if I go back to the minimum, you have the same clusters, the same number of clusters, of course, but the number of trigger cells which has been associated is significantly different. You have few trigger cells which has been clusterized together in the same clusters. So go back to the presentation, and I will conclude. So we implemented a standalone framework to reproduce C++ simulation code in Python. So the stage 2 chain is available and has been validated. We have developed a simplified version of HGCAL, as Bruno presented, and we have available tools for visualizing 3-dimensional HGCAL events, which allow us to test the reconstruction chain conveniently, so standalone, to optimize the current reconstruction chain parameters, for example, the clustering radius, and then it's also easy to develop some new algorithm for the reconstruction chain. So in the near future, we plan to integrate also the bit level emulator in our Python framework to have reproduce with the extreme accuracy the firmware and to proceed with the analysis. Thanks.
Thank you. So let's open the floor to questions. Well, if not, then I have a question. So as I understood it, this is you're testing new algorithms, and as a offline testing framework, are the algorithms, do users write the algorithms in Python, or do users write the algorithm in like C++ strings like our data frame?
So I think I can take this one. So essentially the framework started being developed by the need of running the algorithms quicker, and they were fully translated into Python, which was a bit tricky because I mean essentially it's a relatively easy thing to do until the moment you get to for loops with complex operations which you have to convert to NumPy logic. So all the algorithms that were described are fully implemented in Python.
Like in a vectorized way with NumPy.
Exactly.
Wow.
As much as possible. Sometimes I noticed that some things I wanted to do, it's simply not possible in Python. So for instance, nested vectorizations, if I can call it this way, depending on the operation being applied, cannot be done. So,
right.
But yeah, it was tricky but fun. So.
Do you use Numba at any point?
No, this would be something for the future. Actually, it's a good point. But there's not enough time for everything.
Yeah, even the things that are already implemented, you can fuse operations and you can get them going faster with Numba. Oh, by the way, I just noticed on Zoom that there are some questions. Ben Tovar says no questions, but that was pretty nice. So wanted to pass that on. And then Mina asks, is the module geometry being inserted as a JSON file or channels used in CMS experiment?
I missed the second part. Can you repeat, please?
Is the module geometry being, oh, actually, how about Mina? Can you just ask that? Can you? Because you could follow up better than I could. Mina, are you there? No. Okay, so I'll read her question.
Yes. Oh, hi. So I wanted to ask if the geometry is being inserted as a JSON file or the channels like theta and phi we use to calculate like an atlas or CMS experiment, the module identifiers.
Marco, do you want to answer or should I go?
No, no.
Okay, so I think the answer to your question is that the parameters are stored in a YAML file, and then all the rest is handled with pandas, if I remember correctly.
Right, thank you.
Pandas is enough. We didn't need anything faster because the size of the geometry is well defined beforehand, not like event data. And so it's just fast, at least according to our needs.
Okay, cool.
Right.